Alright, so in this video I'm gonna be explaining another article about domain adaptation, and the title of this paper is Cycles Self-Training for Domain Adaptation. This paper in 2021 by Tsinghua University, the best university in China. So mainstream approaches for unsupervised domain adaptation learn domain invariant representations to narrow the domain shift, which are empirically effective but theoretically challenged by the hardness or impossibility theorems. Recently, self-training has been gaining momentum in unsupervised domain adaptation, which exploits unlabeled target data by training with target pseudo-labels. So because it is unsupervised, so we don't have access to labels of target domain, that's why we use this trick of pseudo-labels. First we create some. Of course it is noisy, but there are some methods to reduce the noise. Then after we created the pseudo-label, the rest of that is just supervised learn. So, however, as collaborated in this work, under distributional shift, the pseudo-labels can be unreliable. As I said, it's noisy. Just like distance supervision, it's very nice, but it's noisy. So, it can be unreliable in terms of their large discrepancy from target ground truth. In this paper, we propose cycle self-training, a principal self-training algorithm that explicitly enforces pseudo-labels to generalize across domains. So it cycles between a forward step and a reverse step until convergence. But what is forward step? What is reverse step? The forward step, it generates target pseudo-labels with source trained classifier. In reverse step, it trains a target classifier using target pseudo-labels, and then here is important, it updates the shared representation to make the target classifier perform well on the source data. So it's a very common paradigm that people use these pseudo-labels. But this article updates the shared representation. So we introduce Sallis entropy as a confidence-friendly regularization, because you can work on that to have a better quality for your pseudo-labels of target domain. So this is the standard self-training. We have target loss, we have source loss. But for cycle training, it's a loop. So you get the target, it continues in a loop until convergence. So similar to the standard self-training, we have a source classifier trained on top of the shared representations on the labeled source domain, and use it to generate target pseudo-labels and for each X in the target dataset. In the reverse step, we design a complementary step with the following insights to improve self-training. Intuitively, the labels in the source domain contain both useful information that can transfer to the target domain and harmful information that can make pseudo-labels incorrect. Similarly, reliable pseudo-labels on target domain can transfer to the source domain in turn, while models trained with incorrect pseudo-labels on the target domain cannot transfer to the source domain. In this sense, if we explicitly train the model to make target pseudo-labels informative of the source domain, we can gradually make pseudo-labels more accurate and learn to generalize to the target domain. Specifically, With the pseudo labels, these pseudo labels y prime generated by the source classifier, we train a target head theta hat on top of the representation phi with pseudo labels on the target domain. And we wish to make these target pseudo labels informative of the source domain and gradually refine them. To this end, we update the shared feature extractor to predict accurately on the source domain and jointly enforce the target classifier to perform well on the source domain. So this is your cycle self-training. And you can look at it as a bi-level optimization. In the sense that in the inner loop, we generate target pseudo labels and train target classifier with the target pseudo labels. After each inner loop, we update the feature extractor phi for one step in the outer loop and start a new inner loop again. However, since the inner loop of the optimization only involves the lightweight linear head, we propose to calculate the analytical form of theta hat and directly backpropagate to feature extractor instead of calculating the second order derivatives as in mammal. I've explained mammal in my playlist for few-shot learning. I think it is third video or number 4. So Thales entropy minimization. Gibbs entropy is widely used by existing semi-supervised learning methods to regularize, to model an output, and minimize the uncertainty of predictions on unlabeled data. In this work, we generalize Gibbs entropy to Sallis entropy in information theory. Suppose the softmax output of a model is y, then the alpha Sallis entropy is this. As you know, when alpha goes to 1, then this entropy converges to this sum, which exactly recovers the Gibbs entropy. So we should say when alpha goes to 1, then our Sallis entropy converges to that traditional Gibbs entropy. It's almost the same. Here you can see Sallis entropy and entropic index. But for alpha equal to 1, as I said, is the standard. What is the standard entropy? It is Gibbs entropy. So we semi-supervisedly train a classifier on the source domain with the alpha Sallis entropy regularization on a target domain from which we obtain target pseudo labels. Then we train another head, theta hat, with pseudo labels, and we automatically find alpha by minimizing the loss of theta hat on the source state. Finally, the optimal alpha hat found, we add alpha hat Sallis entropy. Here we add Sallis entropy. So we update the feature extractors phi. So we update phi. So in forward, as I said, we just generate pseudo labels. In reverse step, we leverage these pseudo labels because we have already obtained them. And then we obtain. But in the update feature extractor, because at the end of the day, you should update the feature extractor phi.